The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Without further ado, I hope you allow me to welcome on the stage our first speaker. And that's Ketan Sampura from Sika. And Ketan, here you go.
Thank you all for coming on time. My name is Ketan Sampura, and on behalf of myself and my colleague Dominic Oetiker, who is not over here, I welcome you all for a presentation on influence of polycarboxylate polymers on sustainability in concrete production. This presentation examines how PCE polymers influence the environmental footprint of concrete at different stages of production. I'm talking about cement production and concrete production. The effects of PCE polymers in concrete production and cement grinding were analyzed in this study, and life cycle and assessment techniques were utilized to assess the impacts associated with the use of PCE polymers. The contents of this presentation are, before jumping on to the contribution of PCE polymers, I just want to mention something about the importance of concrete admixtures in concrete as far as sustainability is concerned, then go on to something related to cement and concrete industry, then go on to the life cycle assessment, and then talk about the influence of PCEs on concrete production or concrete mix design, and then on grinding aids and conclusion. As we know that concrete is a very durable material if made right, and it, as compared to other building construction materials such as wood or steel, if you consider the cost and benefit ratio, cost performance ratio, concrete possesses several advantages over other building construction materials. And chemical admixtures contribute a lot to that. Admixtures significantly reduce the energy consumption during the concreting process, and also source-wise admixtures play and have an important task in the prospect of sustainability. So if you look at concrete admixtures and sustainability from the performance viewpoint and the efficiency viewpoint, concrete admixtures significantly influence the durability of the concrete. And how they do that is, if you take use of, they are able to reduce the porosity of the concrete by using high-range water-reducing admixtures. You can improve the freeze-thaw durability and scaling resistance of concrete using air-infilling admixtures. You can use shrinkage-reducing admixtures to minimize shrinkage, corrosion-inhibiting admixtures, many other types of admixtures to improve the durability of the concrete. In terms of technical solutions, concrete compared to other building materials, as I had mentioned, that it performs much better in many aspects, such as cost and performance, and admixtures play an important role in that. So whenever you're comparing concrete with other materials like steel, or in case of pavement, you're comparing with asphalt, with admixtures, it's possible to make concrete that is much more sustainable if you consider the overall life cycle of the product. If you think about efficiency, using chemical admixtures, you can use recycled concrete aggregates. As you know that recycled concrete aggregates have high water absorption, which will need higher water. You can compensate for that higher water using high-range water-reducing admixtures. Safe ingredients, admixtures usually that are available are safe to use, easy to handle and manage, and not possess any direct threat to humans. And if you talk about energy conservation, you can optimize your concrete mix design by optimizing the cement content of the mix, and hence, contribute to the carbon footprint of the concrete. And you can reduce the energy and time. If you're making like SCC kind of concrete, you don't require any vibration. Or if you're talking about grinding aids, you're talking about reducing energy and also increasing production. If you're talking about use of accelerators, you can use accelerators and reduce steam curing or hot curing. And so these are the ways admixtures usually contribute to the sustainability of concrete. Moving on to the cement and the concrete industry, as you can see over here, during the cement production, in the limestone calcination reaction, 100 kilos of calcium carbonate gives you 56 kgs of calcium oxide and 44 kgs of carbon dioxide, which would be 440 kgs of carbon dioxide per ton of cement. And if you add the other emissions of carbon dioxide from the fuels and related to the electricity and other processes, the total carbon dioxide produced per ton of cement is around 850 kilograms. The production of the cement worldwide in 2010 was 3.3 billion tons, which would mean that if I consider this number, which can be different depending on which source you refer to, it will be close to 2.8 billion tons of carbon dioxide emissions, which is a very, very high number. So how do we do to reduce that number? As per the World Business Sustainable Development Committee and the International Energy Agency, they have developed a roadmap for cement industry to how to lower the carbon footprint of their product. And they have devised a roadmap such that by the year of 2050, they will reduce the carbon footprint of the cements by 18%, or really reduce it by half. And the four main things that they have found out that the way they can do this is by using energy efficiency in production processes, alternative fuel for making clinker substitution by SCMs, and carbon capture and storage. And if you extend this from cement to concrete, then what you can do is you can optimize your concrete mix design and also contribute to sustainability. So in this presentation, I'm going to focus on how you can optimize the energy efficiency in grinding process and at the concrete production level in the mix design using PCE-based admixtures. For that, to find in this study how everything gets impacted by the use of different admixtures and different components, you have to do life cycle assessment. What is the meaning of life cycle assessment? LCA means it is a method to quantify and evaluate potential environmental impacts throughout the product's life cycle. So basically, if I can make something in 5 different processes, when you run an LCA on this, on the 5 different processes, at the end of the day, you can come to know as to with each of these processes, what is the contribution of each of this process to the environment. And then, after considering which process is contributing more and which is contributing less, and considering the economy, I can decide which process I can select. So LCA is allowed to do that. LCAs provide comprehensiveness in 2 respects. First of all, it takes into account all the relevant life cycle aspects of a product, right from the extraction of the raw materials to the shipping and to the formulating and the distribution of the materials to the end of the product, life cycle of the product. And it also analyzes the different environmental impact categories. And what are these, I'll just come to know I'll just mention in a minute. So in this study, LCA techniques were used to assess the impact associated with the use of PCE polymers. The LCAs were run on concrete mix design and on cement grinding. The LCA method used in this study was known as a software called GABI, G-A-B-I. This LCA was performed by our corporate sustainability group in Europe. So over there, the GABI software is very popular because it has a very wide database, and a lot of database information is also from the industry, so it is more relevant. The data sets for modeling were retrieved from the commercial databases, the European Reference Life Cycle Database and the EcoInvent. Impact assessment on the inventory data was performed using 2 methods. One is CML 2001 and one is Eco Indicator 99 method. So what is the CML 2001 and Indicator 99 methods? Are basically methods which will tell you as to if you do follow this process, these are the things you are going to contribute. And I will mention in brief what the method is. So not to confuse you with all these terms, but the CML 2000 method, in here there were 8 categories that were studied and assessed. The first 4 are the abiotic depletion. So not to confuse everyone, I've just highlighted the main words in red color over here. The abiotic depletion potential means the reduction in non-renewable resources. So if I have 2 processes and one process is reducing my non-renewable resources a lot, which means that process is probably not good. And you can do the same thing comparison for different categories. One is the acidification potential, is basically acidification of soil, which will reduce the pH and can damage the ecosystem. So if you have two processes when it's having a higher number than this, that's not supposed to be good. Next one is eutrophication potential. It basically means enrichment in nutrients, and sometimes enrichment in nutrients of something in an ecosystem is bad for the entire ecosystem. Global warming potential is basically the sum of emissions in greenhouse gases. The next four impact categories are human toxicity potential, that is calculated by addition of releases which are toxic to humans. Ozone depletion potential, it's a relative degradation of the ozone layer. Photochemical ozone creation potential is basically indicator of ability of VOCs to contribute to ozone formation. Again, it is harmful for humans and vegetation. And the primary energy demand is basically the quantity of energy drawn in that process. So these are all the 8 impact categories that were assessed when CML 2000 method was used. So for each of this category, I will get a number. Then if I am comparing two processes, I will get a number for this one, for both the process, and I can see which one is better. The other method was the Eco Indicator 99. Again, this is something similar to the previous method, but in this method what it happens is that it assesses the damage to mineral and fossil resources, damage to ecosystem quality, and damage to human health, and it gives an weightage to each of these. So it has given 20% weightage to these, 40% weightage to this, and 40% weightage to this, and at the end you give just one number, single number, with which you can determine which process is better. So this is a better way than the previous one if you are not experienced, because not among all these, not all of them carry out an equal weightage. Someone is more important than the other. So in the Eco Indicator 99 method, you can get the weightage is pre-assigned, so you get a final number which can be easy to compare. And if you want to know what are the details of that Eco Indicator 99, I'm not going to go in the slide, but if you all want, later on you can visit the presentation on the website and find out. Basically, if you see, these are 3 methods, and it goes down back to the extraction of the minerals, and it can find out what is the damage to minerals and resource, and similarly for all the other categories. So what is the life cycle admixture, the concrete admixtures life cycle model that was used over here? In this study, the model used was cradle to gate, which means right from the production of raw chemicals, which were transported to the maker of the raw materials, which transported to the admixture company who formulated the product, and the product was produced. The cost of packaging was added to it, and it gets transported to the production. So this was the LCA for admixtures. Similarly, it can be done for all the other materials such as cement, water, sand, and aggregates. And when you add all that, and it goes to the concrete, and supply the concrete, the building is made, concrete is hardened, it is used, and then at the end of the life cycle it is demolished, and then it is again either goes to landfill or recycling. That will be the entire life cycle of the concrete, which is the cradle to grave. What we are going to focus on is the cradle to grave for the admixtures over here. Because once the admixture gets added to the concrete, kind of its job is done. So moving on to the influence of PCEs on concrete mix design. In this slide I have the cement particles over here where conventional water reducers are used, and as you can see over here, this is a cement particle, and the conventional water reducers have less capability of reducing water. This side over here you have the same with polycarboxylate admixtures. I'm not going to stress too much on that because everyone knows that the polycarboxylate admixtures perform much better in terms of water reduction as compared to conventional water reducers, and in the last decade or so in the US, majority of the high concrete is done with PCE-based admixtures now. So the test setup for this case study was, LCA was conducted on 2 concrete mix designs with the same water cement ratio. Mix 1 was the control and mix 2 was with PCE admixture. The functional unit was 1 meter cube of concrete, and for the mix 2, which had the PCE admixture, all the raw materials used in the admixture and the production processes and the packaging was considered and taken into account. So this was the mix design number 1, which is having a cement content of 590 pounds of cement and water cement ratio of 0.52. For this mix design, it was calculated how much energy was utilized and how much carbon dioxide was emitted for each of the constituent. This is the mix design in kg per meter cube, and these are the ingredients. And if you look at the percent energy consumption of all the materials, you can see that it was highest for the cement, and also the carbon dioxide emission was very highest for the cement. So if you want to improve the sustainability of the concrete, the thing you have to work on is optimizing of the cement. And that's what we did, is we selected the mix 2, which is having a lower cement as compared to the mix 1. Mix 1 had 590 kgs of cement, mix 2 has 472 kg of cement, 118 pounds cement less. The water to cement ratio was same. The workability was compensated by using a PCE based admixture. So the workability was the same, water cement ratio was same, the only change was in the cement content. And now we run LCA on this mix and LCA on this mix. And the results were, for the CML 2001 method, which had the following impact categories. For the mixed design 1, we have these numbers, and the mixed design 2, we have these numbers. If you look at them in terms of percent reduction, if you're talking about abiotic depletion level in elements, then you have 19% reduction in mix 2 compared to mix 1. And so on for all the other categories. And when the other method was used, which is the Eco Indicator 99, which is also similar to 2001, but it gives you an average number, giving weightage to different categories and giving an average number. It was found for the mix 1 was 5.5 and mix 2 was 4.74, which means a 14% reduction in the life assessment. Based on this case study, it was found that mix 2 had an overall better environmental performance than mix 1 in every impact category. In CML 2001, the relative improvement in between 12 to 19% in all the impact categories, and the use of PCE admixtures can reduce the environmental impact of concrete by cement reduction. Now someone would say that this was possible also using any other water reducing admixture, not only PCE based. So what is the big thing about the PCE? So I refer to one case study which was done by a student for his master's thesis at SICA. And what he had done is basically he had selected a mixed design, which having a cement of 506 and 0.5 water cement ratio. And he selected 3 different kinds of admixtures of different bases. And first one was lignin based, second one was melamine naphthalene, and the third one was PCE based. And he added, and all these 3 admixtures were 40% solid products, and he added them to get same workability. So the mixed design was same, and he added them to get the same workability. For the lignin admixture, he had to add 14 ounces to achieve the same slump. For the naphthalene melamine, he had to add 7.7 fluid ounces, and for the PCE, he had to add 14.25. And he ran LCA on all these 3 mixes. And the impact categories he looked at were these 4: eutrophication potential, ozone depletion potential, global warming, and primary energy demand. And the results were as follows. For the eutrophication potential, over here you see this was for the lignin admixture, this is for the SNF and melamine combination, and this was for the PCE. What you see here in the orange bar is the contribution due to raw material of the product. The one in black is due to the process of making the product, the contribution while making the product, and the one in green was due to the packaging required for the product. And as you can see over here, for the PCEs, has the lowest impact as far as eutrophication potential is concerned. Even if you look at the ozone depletion level, the PCEs contributes the lowest. Now I want to point out over here that this was a specific case study which was done at one plant, and it may not be directly applicable everywhere. For the global warming potential, again PCEs perform better than the other technologies. Over here you can see even in the green color, the packaging, the PCE is lower as compared to the other, and the reason for that is because PCEs worked at a lower dosage, so you require lesser of packing material compared to the other ones. And the primary energy requirement also was significantly lower. So from this case study, it was found that PCE admixtures had a smaller material intensity since lower amount of material was required, and the environmental impacts of PCEs are significantly lower than the older traditional technologies. That was about the contribution of PCE polymers in concrete production. Now moving on to the influence of PCEs on cement grinding. Because cement grinding, use of PCEs in cement grinding is relatively newer as compared to concrete production, I will give a small introduction about PCE-based grinding aids. And this is a picture of the typical grinding mill in a cement plant, where you can see steel balls over here. They are used to crush the clinker particles. Cement manufacture is a highly technical process, and every step in the process has a significant impact on the quality of the product, the economics, and also the ecological production parameters. The cement grinding process is the final chance for the cement producer to do any kind of adjustment in the cement quality so that it can meet all the relevant standards and satisfy the customer requirements. If you look at the energy required at the cement plant to do different things, you can see over here that the energy required for a typical cement plant to do cement grinding is the maximum. You require 36% of the energy of the total plant just for the grinding purpose. Second is the clinker formation is 30%, raw grinding was 18%. So if at all you have to work on something, how to improve or reduce the energy, the first would be on cement grinding. And so how do these grinding aids they work? In the grinding mill, when the steel balls are impacting the clinker, there's a crack formed, but within the crack there are these electrostatic charges which again are attracting each other and try to bridge the crack. So, and when they bridge the crack, again now they have to be broken. So that decreases the efficiency of the plant and reduces the production. And the use of grinding aids, what happens is, whenever the crack is formed, the molecules of the grinding aid, they enter the crack and they attach on the positive sign of and prevent the cement and prevent the cement particles from coming and joining together. And that's how they increase the efficiency of the grinding process. The other thing grinding aids do is, because of this electrostatic charges, they tend to form a coating on the cement, on the steel balls, and when that happens, it reduces the impact of the steel balls against each other and also against the clinker particles. So that reduces the efficiency of grinding. Whenever you're using grinding aids, because they repel the cement particles apart, you have less formation of the dust on the steel balls, which increases the intensity of grinding, and you get faster production. The third thing that grinding aids do is, whenever clinker particles are broken, they are again having a tendency to form agglomerates or come together. And whenever you are using a grinding aid, what happens is it basically disperses those agglomerates. The formation of agglomerates, the problem is when the material is grinding and moved to the cement separator, where the cement gets separated, the finer particles goes to the bagging area, and the coarser particles again go for grinding. If the particles are agglomerates, they get rejected because they are considered as one single particle, and they get rejected, which decreases the production efficiency. When you're using a grinding aid, you no longer have the agglomerates, which will increase the production process. So what is the difference between the traditional and PCE powered grinding aids? The traditional grinding aids are based on amines and glycols. The PCE powered grinding aids are based on PCEs and amines or glycols. So I want to make a clear distinction over here that the PCEs used for concrete production are maybe pure PCEs, whereas the PCEs used for the cement grinding are not pure PCEs, but they are PCEs using conventional technologies. But they significantly influence. So as you can see over here, basically you attach PCEs to the traditional technologies and improve their performance. So what happens when the PCEs are used? PCE powered grinding aids are used. In the conventional grinding aid, you have the molecules entering the crack and separating the cement particles. When you are using a PCE based grinding aid, it further enhances the separation, which will give you a faster production and more enhanced dispersion. And as you can see, this is from a cement plant trial. This is a blank without using any grinding aid. This was the production over here. When you're using a traditional grinding aid, the production increased by 13%. When you used a PCE-based grinding aid, it was much higher than that. Same with the specific energy consumption. With the normal, it was 47.6. With traditional, it was 42.6. With the PCEs, was lower. With some of the cements, even though if you use the traditional technologies, you can only get a certain performance. You cannot, even if you increase the dosage, you can't go beyond. But using PCE based, you can get much higher performance. So the advantages are basically maximize of using PCE grinding aids compared to conventional are maximize mill production, enhanced strength development, improved particle distribution, higher clinker replacement. Producers generally don't increase the clinker replacement because when they do that, they'll have to grind it more to get the same kind of activation. But using PCEs, because it improves production, you can go for higher replacement levels. Improved powder flowability and bulk density, and sometimes in tailor-made admixtures you can also have improved concrete workability. So moving on the test setup for the grinding aids testing, the LCA was performed on 3 setups. One was controlled, no grinding aids, and the 2 were with grinding aids, one at a lower dosage, one at a higher dosage. The production output and energy consumption were measured for each setup. The functional unit was 1 ton of ground cement. And for the grinding aid testing, all the raw materials, production and packaging process has been considered. So this was the result. Over here you have in the blue bar the energy consumption and in the yellow bar the production output. So this was when no grinding aid was used. This was when the grinding aid was used. You can see the energy consumption reduced by 5.7% and production increased by 6.25. And when the dosage was increased of grinding aid from 0.018 to 0.035, you had still increased production and lower energy consumption. So when the LCA was run, in this case it was run only with the eco indicator 99. For the setup 1 which had no grinding aids, if that is considered as 100%, then for the setup 2, the efficiency was 95%, and then for the setup 3 it was 91%. So what you can find out from this is that considering eco indicator analysis 99 results, setup 3 had the highest dosage which had the highest dosage of the PCE grinding aid, has the best environmental performance. The PCE-based grinding aid can improve the environmental impact of cement by reduction in energy consumption. And in the conclusion, all I can say is the PCE polymer-based products offer different opportunities to improve the environmental footprint of the concrete at different stages of production. For concrete and cement, based on the LCA calculations, PCE polymers allow for overall improvement in cement grinding and concrete mix design. And for the new development drive, the need of PCEs is based on like new requirements of ultra high performance concrete, blended cements, high SCM replacements using recycled aggregates. With that, I've run out of time. Thank you very much.